So far we've learned how moving charges or electric currents produce magnetic fields, and how magnetic fields in turn can exert magnetic forces on moving charges. But the connection between electricity and magnetism is actually much deeper than that. It turns out that magnetic fields under certain circumstances can also directly produce electric fields. Faraday's law is the name of the equation that we use to describe this behavior, and I'm going to introduce it a little bit differently from how the textbook has introduced it. It turns out that if you have a changing magnetic flux, it will induce looping electric fields around the region. There's quite a bit to unpack here. The first is, what is magnetic flux? Well, magnetic flux is defined the same way that electric flux is, which we saw when we discussed Gauss's law a while ago. Remember that the differential vector dA represents an infinitesimal piece of surface area, and that it points perpendicular to the surface at that position. The flux is greatest when B and the surface are aligned, just like how wind will flow through a window better when the wind can go straight through instead of coming in from the side. And so this really isn't anything new. We're simply talking about the flux of a magnetic field through some region as opposed to the flux of an electric field. One other thing I'd like to point out is that this loop on the integral on the left-hand side is important. It represents that this integral is an integral over a closed loop. So you must end at the same place that you begin. For example, consider a region filled with a magnetic field, a uniform magnetic field pointing into the screen. We can draw a loop. I'm going to make it a circular loop, but it could really be any shape. It doesn't matter. If the magnetic field is constant, so not changing over time, and the loop is stationary, then there is no change in flux through this particular loop. The right side of this equation is equal to 0. So of course the left side is also equal to 0, and the only way for the left-hand side to equal 0 is for the electric field to be 0 along the entire loop. Now let's change our scenario a little bit though, so that the magnetic field is increasing in strength. Since nothing about the area of our loop is changing, that implies that the flux through our loop must also be changing, which means the right-hand side of our equation is now non-zero. And the only way for the left side of this equation to also be non-zero is for the electric field to have a component tangential to the loop, at least over part of the loop. Note that so far this loop is just an abstract idea. We haven't put anything physical there. This electric field shows up whether or not there is an object here. It would happen in the vacuum of space, for example. If we had a region where there was a changing magnetic field like this, an electric field would be generated. And its effects could be noticed, for example, if a charged particle were to enter the region, where it would end up being affected by both the magnetic as well as the induced electric field. This induced electric field, it is an electric field, but it is importantly different from the other electric fields that we've studied. For example, we learned that electric fields, being a conservative field, are associated with an electric potential, and we can define the potential difference between 2 points as the integral of the dot product of the field along some path. This is very similar to the left-hand side of our Faraday's law equation. The only two differences are for the equation for potential, we have this extra negative sign, and Faraday's law specifies that this must be an integral over a closed loop, whereas the path for our definition of a potential difference can be any path. But if we carry out the calculation for potential difference around a closed path, we notice something interesting. The potential difference between a point and itself, which is what it means to integrate over a closed path, we have to end where we started, has to be 0. For example, if we just pick an arbitrary point on our path, if we compute the potential difference along the entire closed loop, we have to get 0, because we can't have two values of potential at the same place. And based on that, this integral has to be 0 always, and yet over here we have the same integral, but it's sometimes not 0. This induced electric field in Faraday's law is fundamentally different from the electric field in our equation for potential, and in fact from the static electric fields created by charge configurations that we've been talking about so far. Electrostatic fields are a conservative field. But induced electric fields created through changing magnetic flux are non-conservative. There is no electric potential associated with this induced field, and moreover, if a charge completes a full circle around this loop, it will have gained energy. The induced field will have done positive work on it over a closed loop. That wouldn't be true if we made a closed loop out of a circuit with a battery in it, because the charge would then lose whatever energy it gained when it went kind of the wrong way across the battery. One way that you can think about reconciling this seeming contradiction is that there are basically two distinct ways to produce an electric field. An electric field can be produced by a potential difference, which is created by a separation between charges, but it can also independently be produced by changing magnetic flux within a region. So this is not so much as an inconsistency as it is simply two different aspects of a field, of which we have so far only really been talking about one. Nonetheless, the effect of the induced electric field on charges is identical to the effect of the electric fields we've discussed previously. Now let's promote this abstract loop through potentially just empty space, and let's say this loop is now a conducting wire. Now the wire as a whole is electrically neutral, and it's not going anywhere, and so the magnetic field is not going to exert a force on this wire, because magnetic forces only exert forces on moving charges. However, once we started to increase the strength of the magnetic field, we induce this electric field. And this electric field is going to push on the charges inside our wire. And it's going to create an electric current, in this particular case, in the counterclockwise direction. Whenever we dealt with current flowing through wires, we pretty much never directly connected that current to the electric field that's causing it. Instead, we relied on the concept of potential difference in voltage because it made it much easier. Voltage is related to conservation of energy, and it means that we only really have to know what's going on at the beginning and end. Whereas to do it in terms of the electric field, we have to integrate over the whole loop, and that means we have to know what the electric field is doing at every point along the wire, and in general, that can be really complicated, really hard to do. So in order to simplify this integral, what we're going to do is we're going to draw an analogy using the similarity of this integral to the integral here for voltage. What we're going to do is we're going to define this quantity here as an induced EMF. Recall that in the context of a circuit, EMF is essentially equivalent to the concept of voltage. It's basically synonymous. As we just discussed, the induced EMF is not a voltage. However, for the purposes of analyzing the current induced in this loop of wire within our changing magnetic field, we can pretend it's a voltage. The relationship between this induced EMF and the current through this loop is going to be the same as the relationship of an actual voltage in a circuit to the current produced by it. In particular, we can relate the induced EMF to the current through the relationship that the EMF is equal to I times R, where R is the resistance of the circuit or the loop. And before we move on, just to clarify, the concept of electric potential is something that can be defined at every single point along our loop. There is a value of potential everywhere along the loop, and so we could then find the potential difference between any 2 points. But EMF, or rather induced EMF, through Faraday's law, doesn't work that way. There is no corresponding potential at every point. The induced EMF applies only to the entire loop, and there is no corresponding analog that we can define at each individual point along the loop. We also need to talk about this negative sign in Faraday's law, what it means and how to interpret it. Consider the same example as before, where we had an increasing flux through our loop, where the magnetic field was pointing into the screen away from you. How did I know to draw the electric field pointing in the counterclockwise direction? To do that, we use something called Lenzs Law, which is what this negative sign mathematically represents. The reason for this kind of strange combination of names for a single equation is for historical reasons. Michael Faraday was the first person to recognize the relationship between changing magnetic flux and induced electric fields. Another physicist named Lenzs, whose first name I forget, was responsible for being able to figure out what direction the induced electric field would be in. And he did so as follows. We note that we have this increasing magnetic field, and so therefore there's an increasing flux through our loop. That increasing flux generates an electric field around our loop or our wire, which in turn generates an electric current in one direction or the other, depending on the direction of the electric field. And that electric current in turn induces a magnetic field of its own. The way I've drawn the electric current, it will create a magnetic field inside the loop pointing out of the screen in the opposite direction of the existing magnetic field. Lenzs realized that the induced magnetic field will always act to preserve the initial flux through the loop. So in this case, the external flux is increasing, and so the induced magnetic field will generate an opposing flux to keep the flux from getting bigger. And since the external field is pointing into the screen and getting bigger, therefore the induced magnetic field has to oppose that, which means it has to point out of the screen. And if the induced magnetic field points out of the screen, we can use our right hand rule. You point your thumb out of the screen and your fingers curl around in the direction of the current, which means in this case counterclockwise. And if the conventional current is counterclockwise, it means the electric field must also be pointing counterclockwise. That's Lenz's law. The induced magnetic field will always oppose the change in the external magnetic flux. It will not typically be successful. It won't be able to make up the full difference, but that is always the direction that it will be in. Typically, the way this equation is used is to find the magnitude of the induced EMF, not caring about whether it's positive or negative, and then using Lenz's law, as described over here, to determine the directionality of the induced magnetic field and therefore the induced current through the loop and so on. So it's going to be very uncommon to actually implement this negative sign mathematically, or in fact, it's going to be uncommon to even really care whether this derivative is positive or negative, because usually, mathematically, all we're going to do is care about the magnitude of the induced EMF, from which we can find the magnitude of the current, and the directionality we can do qualitatively based off of Lenz's law. Before we move on to examples, I want to go on a brief tangent. Faraday's law shows us that a changing magnetic flux, and therefore a changing magnetic field, creates an electric field. And while I'm not going to prove or derive it, it turns out that if we switch E and B in this equation and add in a couple constants, we come to the opposite conclusion as well. Changing electric fields also create magnetic fields. And if you think about it, if the rate of change of the magnetic field is itself changing, so it's not changing linearly, but instead maybe oscillating, then the electric field itself will be changing, because the electric field induced by a changing magnetic field depends on how fast the magnetic field is changing. So an oscillating magnetic field will produce an oscillating electric field. And likewise, an oscillating electric field will induce an oscillating magnetic field. But an oscillating magnetic field induces an oscillating electric field, which induces an oscillating magnetic field, and so on. This was the origin behind the idea of electromagnetic waves. James Clerk Maxwell was the first person to realize that electromagnetism could produce these electromagnetic waves, where an oscillation of either the electric or magnetic field could then produce a never-ending series of alternating electric and magnetic fields. This also represented the first time anyone understood the connection between light and electromagnetism, and in particular, light as an electromagnetic wave. And the way that Maxwell showed this to be the case was when he realized that the product of mu naught times epsilon naught has a very familiar value equal to 299,792,456 meters per second quantity squared, which you might recognize as the speed of light squared. And since it was already believed that light was a wave based off of Thomas Young's double slit experiment, and the speed of light was already determined experimentally, and this was the very first time that that very speed showed up automatically in our equations, and in the context of an electromagnetic wave no less, Maxwell realized this is what light is. He realized, I just found a physical wave phenomena that no one realized existed, and the speed at which this particular kind of wave travels matches the speed at which we've measured light traveling. And so, while physicists already strongly believed that light was a wave based off of Young's experiment, this was really the nail in the coffin. Light was a wave. This was also the beginning of the end of Newtonian mechanics, though, because one of the problems with this is that Maxwell's equations of electricity and magnetism predict the idea of an electromagnetic wave, and in particular, it predicts that these waves travel at a speed equal to what we call c, the speed of light. The speed of a wave is defined relative to the medium through which it's propagating. And so the question then became, well, what medium do electromagnetic waves propagate through? Because they're going to move at this particular speed relative to that medium. And since it was also known that light could travel through a vacuum, for example, outer space, that meant whatever medium light traveled through was weird, somehow intangible. That led to decades of searching experimentally for some kind of evidence or properties of this medium, including the Michelson-Morley interferometer experiments. And after those experiments continually found nothing, ultimately we ended up with Albert Einstein saying, maybe there is no medium, and maybe electromagnetic waves travel at this speed in all reference frames. And the rest, as they say, is history. Now let's move on to some examples, and let's start with a couple relatively straightforward ones. Consider a region with a magnetic field pointing out of the screen and a loop inside of it. If we pull the loop to the right a little bit, nothing will happen at first because the magnetic flux of the loop isn't changing as it moves to the right. Since it's inside an existing uniform field, it doesn't really matter where we put it. But if we keep on pulling the loop to the right, eventually it starts to leave the region with the magnetic field. That means the area through which the flux is passing is decreasing over time, which means the flux is decreasing over time until it eventually reaches zero. As long as the loop is completely within the region with the magnetic field, the flux is constant, so there's going to be no induced current through the wire. But once the ring starts to leave the magnetic field, the flux starts to decrease. And that means, according to Lenz's law, the induced magnetic field created by the ring is going to oppose the change in flux, which means in this case, since the flux is decreasing, we want to reinforce the magnetic field already. We want to reinforce that flux. So since the magnetic field is pointing out of the screen, the induced magnetic fields from the ring will also point out of the screen, and then we can use our right hand rule, pointing our thumb out of the screen, and we find that the induced current has to be counterclockwise. Once the ring is completely outside the magnetic field, if it continues to move, the flux no longer changes, it stays at zero. And that means once the ring is completely outside the magnetic field, the induced current disappears. The induced current only exists as long as the flux through the loop is changing. Another way we could generate an induced current is by setting up the same situation, but this time we could change the size of the loop. Changing the size of the loop changes the area through which the magnetic field is passing. And so more area in a uniform magnetic field means more flux. A smaller area means less flux. So if we start with a small loop and then expand it, the flux through the loop was increasing while the loop was increasing. And Lenz's law tells us that the induced magnetic field opposes the change in external flux through the loop, which means this time, instead of the induced field reinforcing the existing field, the induced field is going to oppose the existing field. Since the flux is getting bigger, the only way to stop it from getting bigger is to oppose the field that's generating the flux in the first place. That means the induced magnetic field points into the screen, and if we use our right hand rule again, pointing our thumb into the screen, our fingers curl around in the clockwise direction, and so the induced current through this loop while it expands is going to be clockwise. Now let's do a more involved example and with some math. Consider a region with a uniform magnetic field of 0.6 Tesla pointing into the screen and 0 everywhere else. The blue square is a coil with 100 turns and a resistance of 100 ohms, and a side length of 0.05 meters. And lastly, let's say that this coil is pulled out of the region with the magnetic field over a time period of 0.1 seconds. The question is, what force needs to be applied to make this happen? You might be thinking, well, if it's moving at a constant velocity, we don't need a force, because if we're not changing its velocity, if we're not accelerating it, we don't need to apply a force. But that's not actually the case. As we pull the square out of the magnetic field, a current starts to flow around the square. And magnetic fields exert forces on current or moving charges. So once we start to extract this square from the magnetic field, there's actually going to be resistance. The first thing we need to do is to figure out what direction the current will flow around the coil. Once the coil starts to leave the magnetic field, the amount of magnetic field through the coil is going to be decreasing, and that implies that the flux is going to be decreasing. And if the flux is decreasing, then the induced magnetic field is going to oppose that decrease, which means it's going to reinforce the existing field. That means the induced magnetic field is going to point into the screen. And if we use our right hand rule, sticking our thumb into the screen, our fingers coil around in the clockwise direction. So the current will flow clockwise around our coil. Now, the right side of our coil is already right at the edge, so there will be no magnetic force on this because it's already just outside the edge of our magnetic field. But the other sides are inside the magnetic field, so we have to think about what directions the forces will be on them. At the top, current is flowing to the right, so if we use one of our other right-hand rules where we point our fingers in the direction of the moving charges or the current, and then we turn our fingers in the direction of the magnetic field into the page or into the screen, our thumb points up. And so the top section of this coil will be pulled upwards. But along the bottom, the current is going the other direction, it's going to the left. And so if we use our right hand rule again, this time we find that the magnetic force on the bottom section is pointing downwards. And since each side of this coil has an equal length and the current through each side is the same, these forces are going to be opposite. So unless they're strong enough to literally tear our coil apart, we can ignore them. They're going to balance each other out. That leaves just the leftmost side of our coil. The current is going upwards along there, so if we use our right hand rule, our fingers point up and then turn into the screen in the direction of the magnetic field, we find that our thumb points left and the magnetic force on the left side of the coil is pointing to the left. In order to get any farther, we need to find the current through this coil, and we can use Faraday's Law for that. If we assume that this is being pulled out at a constant speed, we can change the derivatives to deltas. But we also have to take into account the fact that our coil has 100 turns in it. Each turn has the same flux passing through it and the same change in flux through it, which means we have to take this total change in flux through one of those turns of our coil and multiply it by the total number of coils that we have. Now we can start plugging things in. N is 100. Delta phi, the change in flux, is the final flux minus the initial flux. The final flux is 0, since once it's out of the magnetic field, there's no more flux through it. And the initial flux is 0.6 Tesla times the area of our square, which is 0.05 meters squared. And the time it takes for this change to occur was given to us as 0.1 seconds. This gives us an induced EMF of 1.5 volts, and we can calculate the current generated by this induced EMF as the EMF divided by the resistance. And in order for the coil to move at a constant speed, the external force applied has to be equal in magnitude to the magnetic force on our coil. That's equal to the total charge moving along that section of our coil times how fast they're moving times the strength of the magnetic field. Normally we would write the total charge moving along that section as the number of electrons times the charge of an electron. But we're dealing with a coil with 100 turns in it, so it's easiest to represent this as the number of electrons per turn times the charge of an electron, and then multiply that by 100 to get the total amount of charge moving along the vertical stretch on the left of our entire coil. We can represent V as the distance the charges are moving divided by the time it takes them to move that distance. We could choose any distance and time as long as they match up. The easiest distance to pick here is the length of the square over however long it takes the charges to travel that full length. Now, if you think about it, the number of electrons per turn of the coil times the charge on each electron divided by the time it takes them to travel the length of that side of the square is just another way of describing the current through each turn of the coil. We know what the current is, we found it, and we were given L and B, and when we put this all together, we get 0.045 newtons. An alternative way of solving this power is in terms of energy instead. We can say that the energy used to maintain this current for 0.1 seconds is equal to the power required to maintain it times how long we maintained it. And the electrical power can be expressed as I squared times R. And we know I, we know R, and we know T. And so the total energy required was 2.25 times 10 to the minus 3 joules. That energy was put into our system by this external force that's causing the coil to move in the first place. And the work done by a constant force is just equal to the dot product of F with D. F in this case is the external force that we're looking for, and D is just the distance that we moved the coil through the magnetic field, which is 0.05 meters. And if we rearrange this equation and plug in the energy we found in the previous step for the work and 0.05 meters for D, we find once again that the external force is equal to 0.045 newtons, just like before. It's also worth mentioning that this energy we calculated is often called the thermal energy dissipated by this process. After all, we put that much energy into the system, but it didn't go into speeding up the coil at all, but rather it was used up in the process. So in the end, this coil would be hotter than it was when it started. Let's look at another common setup for these kinds of problems. Once again, we have a region with a magnetic field, and in this case, the blue lines represent wires or rails, and then the rectangle represents a rod that is free to slide on top of the rails. All of these things in blue are conductors, which means current can flow through them. There are a lot of things that we can do with this kind of scenario. For example, if I were to pull on this rod and move it to the right, I would be increasing the flux through this loop. And if I'm increasing the flux, I'm going to create a magnetic field that's going to oppose the existing field. And to do that, I would have to generate a counterclockwise current through the rectangle that's connected, including the rails and this conducting rod that can slide around. So if I pull this rod to the right, I will generate a counterclockwise current through the left sort of completed part of this circuit. If I were to push it to the left, on the other hand, the flux through the completed part of the circuit would be going down, and I would end up generating a clockwise current, which would in turn reinforce the existing field. So we can generate a current in this kind of setup just by pulling the bar to the left or to the right. If I want to generate a larger current, I pull it faster. If I want to generate a smaller current, I pull it slower. I'm not going to work through a whole example of this with you, and there are lots of different variations of this kind of problem. But we'll discuss sort of how you would start approaching this, how you would deal with the geometry, and so on. So first of all, you would often, whether you're given it or not, you would often at some point end up dealing with the velocity of the rod. How fast is it going? To calculate the flux through the part of our closed circuit, we need to know what the area of it is. The area can be expressed as the vertical dimension of our rails times x, where x is the distance from the left end to the position of our rod. Now in this case, the magnetic flux is changing because the area is changing, which means we have to deal with the dA part this time. Luckily, it's pretty straightforward. L is constant, and so dA is simply equal to L dx. And dx is how the position of our rod is changing over an infinitesimal amount of time dt. And that can just be expressed as v dt. At any given moment, the flux through our little circuit is just b times a, and the induced EMF is the time derivative of that. And if we plug in dA from above, we end up with the induced EMF is equal to BL times V, where V is the speed at which the rod is moving at any given time. The trick is part of this kind of problem is usually just working out how all the geometry relates to each other. But once you've done it once or twice, it all tends to be more or less the same. Now, there are other variations of this kind of problem. For example, instead of pushing the rod left or right to generate a current, imagine we instead put a battery on our rails. This battery will generate a clockwise current around our loop, and therefore a current pointing downwards through the movable rod. Using the right hand rule, pointing your fingers downwards and curling them in the direction of the magnetic field pointing into the screen, we get a force on the moving rod pointing to the right. But as the rod moves to the right, the flux through our loop increases. That will generate an induced EMF that opposes the increase in the flux through it, which in this case will generate a counter current pointing the opposite direction as the one created by the battery. The rod will speed up at first because at first it will be moving very slowly. The force has only just started to accelerate it. So as it moves slowly, the flux increases slowly, which means the induced current will be very small. But as the rod speeds up, the induced current increases. And eventually the induced current will match the current provided by the battery. And once these two currents are equal, there will be no actual current flow in this rod. And if there is no more current through this rod, then there's no more force on the rod, and it will no longer experience a force. It will not come to rest. It will continue moving at constant velocity. This is another way that terminal velocity comes into play. So another great question that we can do with Faraday's law is we can ask, what is the terminal velocity of a rod in this kind of circumstance? This is, by the way, the basics of how the concept of a railgun works. You have rails with a strong power supply of some kind on them, and you have a conducting object to bridge those rails, and the object will be accelerated and flung out one end of it. And the stronger you can make your battery, the higher the terminal velocity will be, and the faster your projectile will end up going. There are lots of other things you can do to make this work better, but this is the basic gist of how a railgun would work. Last but not least, we're finally ready to understand how we can easily generate an alternating current. All we really need is a permanent magnet and a coil of wire. So as you can see here, we have a magnetic field pointing from the north to the south pole. We have a coil of wire within that field. One end is connected to something that allows us to spin it. It could be a hand crank, it could be a turbine of some sort. If it's a power plant, it's probably a steam turbine or maybe a water turbine. And then on the other end, the two ends of the loop, one of them basically brushes against the inside of something over here that's connected to one of your output ends, and the other end is kind of inset a little bit so that it brushes against the outer loop, ring over here, which connects it to the other terminal of your generator. As you rotate the coil, the angle between the magnetic field and the area of the coil changes, and that causes the flux to change. If we assume that the coil is being spun in a simple sinusoidal rate, then we can replace theta with omega t, where omega is the angular frequency of rotation. Evaluating the derivative, and we find that the induced EMF in our generator becomes the magnetic field strength times the area of the loop times the sine of omega times t. Note that the faster you spin it, the greater the induced EMF would be. We can also increase the EMF by basically using the same trick as a solenoid by layering this loop so that we're not spinning one loop, but we're spinning many loops. And that allows us to multiply our EMF by however many loops there are. However, it comes at the cost of making it physically harder to spin. This simple idea is the basis for the generation of the vast majority of electrical power that we use. We use turbines to convert mechanical rotational energy into electrical energy using this very simple concept. And even like very expensive and very powerful generators, they still operate on the same basic principle, even if they look a little bit more complicated. Faraday's law and electromagnetic induction in general form really the backbone of modern technological society. It's what enables us to easily generate electrical power. It's what easily allows us to harness electrical power and convert it from one form to another, or even, as we'll learn later, convert between high and low voltages or high and low currents and so on.